Hello, welcome. My name's Phil Winder, and this is another episode of our presentations for Winder.AI that we do that talk about the work that we do, the stuff we're working on, things like that. And you've joined me in the middle of a presentation that I started last week. And this is the second presentation in that series. It's all about reinforcement learning. It was the tutorial that I gave at ODSC London. And unfortunately, that wasn't recorded, so I'm repeating it here just for posterity. Today, we're going to be, actually, just as a bit of a recap first, if you didn't see the first one, previously, in the previous video or the previous presentation, I talked a lot about what RL is. I gave a lot of introductory material, sort of introducing the ideas and the concepts behind it, some intuition involved around it, but it was still quite high level. I did talk about a few examples, but I didn't talk about how they were implemented or anything. It's just very high level sort of RL overview. In this presentation, I'd like to talk about some technical topics this time. So I'd like to talk about things like how you actually go about designing an RL solution, which is from one of my earlier talks, but there's a few other bits and bobs as well about when you need to go deep, and other things such as safety in RL, and I'll touch on a few subjects. Really, it's a bit of a smorgasbord of RL topics. It's probably a bit higher than introductory material. It's kind of like intermediate material possibly. So it would benefit if you had some RL intuition already. But if not, feel free to keep watching. Feel free to ask questions. As always, if you'd like to ask any questions, then writing out the comments in the software that you're using. So if you're on LinkedIn, then just send a comment. If you're in YouTube, just send a comment, so on and so forth. I'll come back to that at the end. I'll loop back around and I'll see if there's any questions. So apologies if you do ask a question and I miss it. But I will get back to them at the end. Anything else? Oh yeah, so high level stuff. So obviously, if you are looking at working on an RL problem yourself and you need some help doing that, then reach out to Winder.AI. You can find out all about us and what we do on our website, Winder.AI. My name is Phil. You can reach me at phil@winder.ai over email. And if you're just interested in the technology side of it, then I definitely recommend my book, which is by O'Reilly. It's called Reinforcement Learning, and the website for that is rl-book.com. I think there's probably a link later in the slides. I think that's it. All right, let's crack on. All right, let's figure out how best to do this. That looks okay. Right, I'll keep my face on. I'll remove it if it gets in the way. All right, so let's recap what an RL problem is. We touched upon this last time, but it's worth going over it again. Just have a think about what an RL problem is. So an RL is just one of a few different implementations that attempt to solve a Markov decision process, or attempt to be optimally solve a Markov decision process, an MDP. And so when we say an RL problem, what we really mean is what is an MDP, and how does that fit into real life? In general, RL problems tend to be sequential. They go around in circles. So you perform an action, it affects the environment changes, your perception of that environment changes, it comes back to the agent, and it then decides what to do next based upon what it's observing, produces another action, goes back to the environment, so on and so forth. Keeps going like that. So that's one way to think about it. The other way to think about it is in terms of trajectories, which are the paths taken for one individual set of one specific incantation of that loop. Incantation, that's a good word. It's like, yeah, witchcraft. But if you imagine that loop rolling out, if you roll out that loop, you make a decision and then there's a fork in the road. You take one of the actions in that fork. So you go down that path and so on and so on and so on. And you end up with a trajectory that kind of forks off. If you do that many times, you end up with some kind of like a tree-like pattern as you're exploring more and more of the environment. So you can think of sequential in the sense that you have to make decisions in a loop. It's a reactive, strategic like decision-making process. But you can also think of it in terms of sequences or trajectories as well. And if you can imagine a problem that a potential trajectory could go off in many different ways to form this tree-like structure, then again, that's a good indication that it would be optimally solved by an RL solution. Related to that is strategic. So the types of things learned are not necessarily the one perfect path through that maze. Although sometimes some problems do apply RL to find the one true solution. Most RL problems actually are a bit more stochastic. So even in like the game playing examples where, you know, the chess, the Go, all of those examples from 5 or so years ago, those environments are entirely deterministic. You know that if you take your chess piece and move it to the next square, you're moving it to the next square. It's going to land on the next square. It's not going to randomly not get there some part of the time. Like if you're in the real world and you tell a robot to go, you know, turn left, it might not actually turn left because its wheel's stuck or whatever. But even in those situations, there's never one well-known path to victory. Usually there's lots of different strategies that you could pick, and it's all about picking the right strategy at the right time. And that's going to change on every single step. You might pick one strategy on the first time step, which leads to one action, moving a pawn, but then you might decide in the next time step that maybe that was wrong. And it usually doesn't sort of really, it's not as mindful as this. It doesn't know that it's done something wrong at that point. All it knows is that actually in this situation, given this observation, there's a new strategy that is more optimal than the previous one. And so it might go off in a different direction. It might move the bishop or something. So even in very deterministic scenarios, there's still a wide range of possible strategies. And that gets even more complicated when you have non-stochastic environments, which is a situation where random things can happen. So the point there is, yeah, strategic decision-making problems are a good problem to have for RL. And compare that and contrast that with a single one-shot decision-making scenario, which might be better off solved by machine learning. Within the problem itself, you have a number of domains, and you have a domain, and within that domain, there's different pieces of the puzzle that you need to decide on really early on to kind of provide you with the architecture of the MDP. The thing that's performing an action is usually an entity. It's usually a physical entity like a person or a robot, or it could be a software agent which is representing an entity, but it's thought of as a thing, and that's why it's called an agent. It has agency. It has the ability to take its own actions and learn from it. When you actually, if you're looking for entities that are performing an action in real life, it's a great place to start looking at people. Where do people make these decisions? Are there people making strategic decisions all the time? Could we help them make those decisions? Could we help make those decisions more observable? Could we fully automate those decisions? Another place that you might look is in a current control system, especially in an industrial process. We've worked with a few companies that have had advanced process control systems, ABC systems, which are basically, you know, fancy, control systems, and they control valves, they control electronics. They usually typically control PID controllers. PID control is a well-used, a well-documented, stable form of control algorithm that needs to be tuned, but eventually, you know, optimally sets a valve to a specific point, or sets a certain amount of material to be produced at a certain point in time. So it's a way of controlling things. So if you're seeing these, then again, that might be an indication that RL could take over in that process and optimize or automate some of those controls. In terms of the environment, you're looking for a bounded context. That's a software engineering terminology, domain-driven design, if you're interested. A bounded context is something where you have a domain and it has boundaries. So, for example, if we're talking about an industrial control problem, if we're talking about an oil refinery, for example, there's a very sort of distinct bounded context on what is necessary to use as information in that system. So, for example, the last night's football score is not part of the bounded context that needs to be. It's not part of the bounded context that is an oil refinery. So you need to figure out like what things are included, what things are excluded, and this is usually the basis of the observations that you will look to try and get into your system. Because remember that you're trying to, even though you usually can't see the true state of the environment, you are trying to get a good observation of the environment that gets you closer and closer to that true state. So usually this bounded context gives you a good indication of what is useful and what is not useful. It's also important that the environment is affected by the action, and that effect is observable by the agent itself. Because if you're in a situation where nothing changes when the agent does something, it can be really hard for the agent to figure out which action actually led to a successful result, because the action didn't actually change anything in the in the environment. So there's a couple of, and that does actually happen sort of naturally. That happens in real life, and a couple of ways of getting around that is firstly, always try and find observations that do change when your agent produces an action, and that could be as something as simple as incorporating previous states or previous actions even in the next observation. It just allows that state space to be better represented in accordance with the actions that the agent can perform. The rest of them are all a little bit self-explanatory. The observation we obviously need, but it kind of emerges from the environment. The action we obviously need, that emerges from the problem definition. What you're trying to solve, what can the agent actually do? Yeah, the interface. Actually, that's quite a key one. It's quite enticing to think about many problems that could be implemented or automated, rather, by RL. But in order to actually do it, you need to interface with it. So you also sort of need to look for places that already have good APIs or good external sort of access to those systems, good logs, maybe good historical information, good documentation, good understanding of that domain. If you don't have any of these, then that can make the problem twice as hard, because you're basically perpetually waiting for data. You're perpetually waiting for access to these things, and that can significantly delay a project. And finally, the reward. So you need a situation that has as clear as possible. I was going to say just clear. I was going to say a clear definition of something, but it's never clear in many situations. As clear as possible, a definition of success or failure, and that has quite a wide range of potential values that you could assign to success and failure. We'll talk about that just shortly, but fundamentally, you need to be working in a situation that can have success or failure. If you don't, then what are you doing? Like, it doesn't need to be automated. Okay. So now I'm going to go through so these numbers here, they loosely relate to the order in which you should look, the order in which you would do work in order to develop an RL solution. And they're ordered in the sense that if you do the first one first and find that you can't do it, then there's no point doing 2, 3, 4, 5, and 6. Okay, so they're ordered in terms of dependencies. But they're also ordered in terms of what we have found to be the most useful things to do first. Like how much can we learn? How much can we de-risk the rest of the project by doing those things up front? And so in essence, the first one here is the most important step in the entire journey. And that is related to what we were talking about just previously. And that is developing the environment and learning about the environment. And it's profitable because it's akin to doing the exploratory data analysis phase in a traditional data science project. I say traditional now because the EDA process in a ChatGPT project is basically just throw a load of prompts at GPT and see what it does. But in a traditional data science project, the EDA step is quite profitable because it allows the data scientist to become familiar with the domain and familiar with the problems and understand the data and the descriptions of the phenomena that are involved. Developing an environment is very similar, but for reinforcement learning. And when I say developing the environment, that could take a couple of forms depending on what angle you're kind of attacking the problem from, and it depends on what you've found in your prior research. The traditional RL problems begin with a simulation, and that often comes from a simulation that has been used for a long time and has proven to work quite well. So a lot of domains have simulations that are used often. Others come from sort of physical models that have been proven from first principles. Some require a bit of work. Some require a bit of development. You have to combine and merge and work with different models and develop new parts and things. And that can be challenging. You can take historical data and learn models. You can train an algorithm to behave like that underlying physical model. And make that into a simulation. So, imagine imagine you're building an RL solution for looking at cat pictures or something like that. You could use a generative image algorithm to generate cat images for you, and that could be your simulator, for example. That's a pretty bad example, actually. But basically, you can use generative methods and train them to produce the dynamics of the system that you're trying to simulate. And also, of course, don't forget real life. If you are lucky enough to work in a domain where the impact of an action is both low risk and high reward, then you can just try it in real life. Those situations tend to happen in the tech industry. They happen in, when you've got users using websites and things like that. If they're recommended a product that is not ideal, it's not the end of the world. But, if it's for the purposes of doing an experiment, if it's the purposes of teaching your agent how to learn, then it's probably, a no-brainer. Just do it in real life. You can use A/B testing and all the other good deployment strategies. But then, so they're all sort of subjects about developing a simulation in order to train your reinforcement learning in. And simulations are incredibly useful because, like what I said before, they help you understand the domain, but also they can not only be used for training the agent if it's a good simulation, they can also be used for testing it and evaluating it as well. So even if you're using another method to train your algorithm, I still recommend attempting to build a simulator of sorts, just for the purposes of testing, just for sanity checking, even if it's just a really simple noddy environment that is not really related to your domain at all. It's a very good unit test of your algorithm. So I still recommend you go through the process. And then you get to like the other sort of less traditional RL methods. And the first one, but the most powerful one, is offline reinforcement learning. If you find yourself in a situation where you have a large amount of log data or of data at hand based upon previous interactions, previous decisions, say you're part of a customer service process and you already have a good sample of the trajectories of various customers, that they have taken when the customer service agent has like taken an action, like maybe sent them a text message or sent them a call or something. And then the customer has then done something and their state has changed. If you already have a good large amount of log data for that, then you can use offline reinforcement learning to train your algorithm. And the way that the offline algorithms work is that they basically another word for offline RL is often called imitation learning, and it's basically a process of watching what did happen and kind of learning the model through observation. Now, it works really great because you don't have it, because it's from real data, usually from real life, and therefore there's no biases involved. Like that is real life. It's not, the problem with using the simulation often is that it's not truly representative of real life. So if you train it in simulation, then try and use it in real life, it doesn't perform as well. With offline learning, it is using real life data, so you don't have that bias there. But one of the challenges is that the agent can only learn from the observations that it actually sees, just like any machine learning algorithm. If you don't have a trajectory represented in your data set, then the RL algorithm, it doesn't know about that. It can't know about that. So that area of this tree, think of it as a tree again, of these trajectories, that area of the tree is blank. So the RL models, especially the ones that have approximation, they're relatively okay at kind of smoothing over those blanks in the data in the trajectories, but they can't work miracles. Like if you've got a huge gap which is hugely expressive with loads of actions and loads of states, like the RL algorithm will have to visit those states in a random fashion again to explore them in order to figure out, well, actually, are those, like, why haven't they been explored? They may be the most optimal trajectories. So that's that. And then there's learning from humans, which is largely just an extension of offline RL. Again, it's imitation learning or curriculum learning, it's sometimes called. It's basically the idea that you're trying to take well-known and effective strategies and apply them to the RL agent and tell the agent that it should. I just realized that you can't see that step. I'll just move that away for a second. It's the idea that the human has learned these optimal strategies and they know that that's the right situation to be in. So you might as well learn from it again. So it's a lot like offline learning where you're attempting to force, you're attempting to force the agent to follow these trajectories. And you do that by sort of manipulating the weights so that it does copy these trajectories. Okay. So once we've moved past the first part, which is understanding the environment and understanding attempting to present a good simulation, then we need to figure out whether we can observe it properly. And the next sort of most important phase here is what I call state or observation engineering. And it's not really talked about so much in the literature or in the books, but it's akin to, it's similar to feature engineering, but it's not feature engineering. I'll talk about that in a second. But it's also not policy engineering either. So just to recap terminology here, the policy is the technical name for the model that is making the decisions based upon the observations that it sees and the actions it has at hand. And it has an internal, learned memory of what happened in the past and which actions are the best, and that it just picks the best actions again based upon the state. So the observation engineering here there's basically two elements to it. The first one is, if you remember, the goal is to try and create an observation that is representative of the state. It doesn't necessarily have to be the state. So, for example, in many situations, you have a video camera, and a video camera is a very good representation of real life. It's not quite the true state of things, depending on the things, because the camera has always got one field of vision. So it's quite common to have like, areas where the thing that you're actually interested in is actually blocked by something else. Happens all the time in like autonomous vehicles and stuff. So that's a challenge. Yeah, and so on and so forth. But the problem with using a video camera is that the amount of information actually contained within that image is huge, and that's just one image. So, we're usually talking many, many megapixels now with modern video cameras, and it's not just one set of many megapixels. It's 24 or 30 sets of these megapixels every single second, and you've just got a bit of a processing challenge there. How do you deal with that sheer amount of data? Well, it's quite likely that even though a video is a reasonable representation of the state of the system, it's probably very lossy as well. There's a lot of superfluous information that is not relevant at all. And so what you can do is you can start looking for other observations that are simpler versions of the same thing, but have just as much informative power. There was an example of a paper where they were training, it was a robotics task, I can't remember what specifically, but they found that if they just included a really simple sensor to tell the agent the height of the robot arm off the table. So like, this would be 0 and this would be 10, this would be 20 or something like that. A sensor to give that single value, that caused their policy to be much more robust, the training to be much easier, so on and so forth. It's a much more information dense observation signal than a video camera that contains a lot of superfluous stuff that is not relevant. Another thing that I've used to quite good effect is autoencoders. So, let's make it more general than that, but basically dimensionality reduction. So remember, we're not trying to reduce the amount of, we're not trying to hide, what's the word? The reason for doing this is purely for computational efficiency. If you can reduce the dimensionality of the data, reduce the amount of information going into the agent, then it will train faster, it'll learn faster, it'll make the model much simpler, so on and so forth. So it's always a good thing to do. What else have we got? Yeah, we've got one here, which is forward models. So in a few domains, especially if they're sort of physical and industrial ones, there are experiments that you can do that allow you to learn the forward model of a system, which is where you see an observation and it's a representation of the true state, but it's not the true state. But you can perform experiments to learn the transformation of the true state into that observation so that you can effectively invert that in a function. So for example, if your task is to detect people clapping for some reason, then what you can do is you could have a microphone and perform an experiment to see how strong a clap is right next to the clap. But if the observation is from a camera, like you can see now, you don't really know how strong that clap is. But we could probably measure the speed at which my hands are coming together and how far away I am from the microphone or whatever. And we could take the measurements done by the local sensor, the microphone, and whatever else is involved, and then create a model that then sort of effectively predicts what the true state is based upon the images that you're seeing from the camera. Not a great example, but I hope you get the idea. Then you've got, so again, remember that the whole goal of this is to attempt to better represent the true state of the system so it can use that information to make better decisions. Quite often, there's just a lot of experimentation involved. If you have access to lots of data and you don't know what data is useful and what data is not, fortunately, there's a lot of, brute force grid search style, let's just try this type experiments. So what that means is that it's quite important to have a good, if you are doing this repeatedly and on an ongoing and iterative basis, it does make sense to invest in the MLOps part of the problem, making it easier to do these experiments and to manage them and to record them and stuff, rather than just trying to do them on your laptop on a script. Yeah, okay. I think that's good enough. All right. What's next? Okay, so next, policy engineering. So now we've moved past the observations now. We're now looking at the policy, and the policy has to do several things. Again, this isn't talked about too much in the literature, but the policy has to do effectively three things. It has to take the observation as the input. It then needs to convert it into something useful that the policy can actually use. Then there's a policy model that needs to learn and remember possibly, and there's all sorts of structures that you could use in there. That could be any ML algorithm basically. And then there's another conversion step on the output. There's the sort of the actual, I call the action conversion. And this is where you're taking the outputs of the model and then turning them into useful actions at the output. So let me just give you a couple of examples of all that. So I think the most common example that you'll stumble across is on the state conversion side, is that he'll have observations in various forms, video cameras, audio, machine settings, whatever. But most of the time, you're probably going to be using some sort of deep learning based policy model. And that's arguably a good thing or a bad thing. But the point is that they always expect, and they still do to this day, they expect a very well normalized input. So it should be ideally normally distributed and standard deviation of plus or minus 1. Depending on kind of what activation functions you're using and things, there could be other requirements there. Some of them are like between 0 and 1, some of them between -1 and +1, so on and so forth. But generally, if you've got them centered around 0 and plus standard deviation of plus or minus 1, then it'll work pretty well. Now the challenge is the vast majority of data, raw data, does not look like that. Pixel values are like intensity values, they're counts. Sensor values again could be anything. They could be really big, they could be discrete, they could be any number of things. So you have to go through a sort of traditional-ish ML like problem of feature engineering at this point. You're trying to convert the input into a thing that's useful for the model. On the action side, this actually has a little bit more to do with the definition of the model, actually, So on the action side, you've got the two sides to it. You've got the output from the policy model, the output decision from the policy, and then you've got the actual action in real life. So, for example, a lot of algorithms represent a continuous action. So, an example of a continuous action might be to set a valve to a number of degrees between 0 and 360. And that's a continuous number because it could be 35.7 or it could be 178.254, whatever. So it's a continuous number. And the way that these things are normally represented is by the summary statistics of a statistical distribution, quite often a normal distribution. So rather than outputting the actual value, these models will output the mean and the standard deviation, and then you actually have to sample from that distribution to get the final value. And in these models, they try and find like they try and optimize to find like narrower and narrower standard deviations. So ultimately it almost becomes like it is predicting an actual value. But it's really important to actually do the sampling because that's part of the exploration of these algorithms. They need to kind of not just try the mean value all the time, but also try the values that occur like either side of that distribution, just in case that one is better than the other one. So it's just a form of sort of natural exploration. So that's just one example of that. Okay. So let's just step back a little bit and talk about a few of the common observations that you might see. Basically, they usually come in the form of discrete observations or continuous ones. You can turn continuous states into discrete states with things like binning and coding and hashing and simple classification models. Is it greater than 50 or less than 50? Things like that. So you can turn them into discrete states or observations. But the interesting thing to note is that the continuous states are generally harder to solve. It effectively makes the state space infinite because you don't just have to try like a value of 0 or 1 on an action now. You need to try every single possible value across this continuous number line. So it does mean that continuous, especially with continuous actions, because remember on the policy model side, we're usually using some kind of function approximation, and that deals quite well with like continuous inputs. But on the action side, the actual on the output of these things, it's got to actually try all of these different values in order to figure out which one's the most optimal. Yeah. Oh, yeah. And actually, theoretically, there's still no convergence guarantee for an RL algorithm there. In fact, RL algorithms in general, especially when you're using neural networks, there's still no theoretical proof that they actually work. There's only a proof for the sort of simple discrete case with no approximation, or at least a limited amount of sort of linear approximation, and that's proven to converge. All right, that's enough of that. Oh, I've accidentally talked about the next one already. So here we're just talking a little bit more. Let me make it a bit more visual, make it a little bit more, there you go, a little bit more entertaining. Here I'm talking about the actions a bit more, talking about the possible actions that you might see in the output. If they're binary actions, they're easy to work with, makes the action space small, it makes it easy to explore because you've only got 2 things to work with. Yeah, talked about that. Oh, one thing we didn't talk about is options framework. So quite often in situations, you need the ability to, also masking as well. That's not in this list. In many situations, you need the ability to select no option, and that's fine. It basically just forms another action effectively, but it's got a technical term called the options framework. So you can just go and do some research on that if you're interested in that. But basically, the idea behind it is having an extra action to denote that the agent wants to do nothing. It's just going to sit there and not perform any action. And that's very useful in many situations like, trading bots and things. You don't want to do a buy or a sell. They're quite happy with what they've got. Then you've got what I mentioned, masking. In many situations, it makes it easier and simpler if you can reduce the search space by masking actions, saying that only certain actions are allowed at any one time. It tends to be quite hard to do this in practice, though, because the masks could get really complicated if you've got quite a complex action set. But there's usually some heuristics and some simple sort of hand-coded algorithms that you can use to automate that process. It really helps with sort of safety and constraint sort of driven development here. If you need to ensure that machines don't go out of spec, or if it becomes unsafe or whatever, you can just mask that off from the agent. Ranked options. This is where, you have, in many cases, it makes sense to provide recommendations effectively. And there's kind of like slates of actions rather than just one action. There's been quite a lot of work in attempting to formalize the ability to produce a range of options rather than one. So let's talk about in general a little bit now. So in general, I always recommend just keeping it simple to begin with. Start with something simple. Start with the simplest possible environment, with the simplest possible set of observations and actions, and make it work on that first. Because if it doesn't work immediately on that, you're going to have a hard time making it work on something more complicated. Many algorithms expect a specific type of data. So this is why you kind of see data scientists and engineers kind of getting used to using the same algorithms over and over again, because they know the assumptions, they know the caveats. And as soon as you switch to a different type, there's a whole new set of assumptions and caveats that you need to learn. Okay. Exploration is one area that tends to be a lot more domain specific, to be honest. I would always recommend, I think I'm going to sort of skip this slide quite quickly, actually, because this is already taking a long time. We've already been 40 minutes, so I apologize if we've still got quite a bit to go as well. Most implementations do absolutely fine with a really simple exploration strategy, just a random exploration strategy. So some proportion of the time you try a random action, and you can make that a little bit more complicated by, like, if you're happy that your environment is relatively stable, you don't have to keep randomly trying actions. You only need to try the actions that you haven't visited yet. But there's lots of really interesting sort of analogs to human behavior here, and I won't go through all of them, actually, but there was one example at the bottom here, and it's just a screenshot from a paper where they took a previous exploration type that was sort of thought to be the most advanced and the most high-tech exploration that you could possibly do, and it turned out, yes, it was like, basically like there was this surprise, and basically they hacked that exploration algorithm where they put a TV with just a panel that just changed images every couple of seconds, so that an agent that was attempting to explore in this environment just kind of got stuck on the TV, because it was using this, I think it was this one, it was the information gain. It was using basically how much surprise is there in this new image? How much did I expect to see this next state? And the TV was just scrolling around and scrolling around and scrolling around. It was all new to the agent. So it just stood there watching TV. So that's quite a fun analog to real life as well. Okay, then we come to rewards. Yeah, and this is quite important. So let's spend a few minutes talking about this. Fundamentally, the definition of any reward should be, well, let's start with the right hand side. It should be simple. It should be simple. If you go down the path of making it too complicated, which is sometimes necessary, but if it gets too complicated, you can't understand it, and it's really easy to accidentally hack, sort of attack your own algorithm by providing it with a reward that the agent is better at solving than you are. The image on the bottom right here is an example of a simple experiment in Unity, in the 3D gaming framework, where the goal is for that little blue blob, I don't know if you can see it, but little blue blob to kind of jump over that see-through barrier. It can, and it did, and it is able to learn to move that white box towards the barrier, jump on the box, and then jump over the barrier. But it found it was much easier to just kind of sneak around that tiny little edge that you can see on the side of the barrier there. So in many cases, it just simply walked around the side, simply because there was a tiny little edge on the side there. So yeah, expect your agents to kind of learn these hacks. That's what you're asking them to do. The best way to avoid that is to make sure that the reward is simple, because otherwise it's not even the fact that they do this. It's really hard to spot and see when they do this if your reward is complicated, or if your problem is complicated. It can be hard to see. It's easy to see in this case because we can literally see the agent going around this barrier, but in the vast majority of problems, you can't see. You're reliant on metrics and other sort of observational signals, which are much harder to interpret. Of course, the reward should also match the business problem. We talked about this ability to we talked about this idea of having a clear definition of success and failure. And yeah, really that's all about being matched to the business problem. If the business problem doesn't have a clear definition of success, then you probably shouldn't be working on it in the first place, irrespective of what technology you're using to implement it. It's much easier to work on something when the end state or the goal or the business problem is clearly defined. So what your goal is really as an engineer is to find proxies to that business problem. Like, what metrics can you come up with that are proxies to the real life business problem? And ideally, actually, you could probably just use the business metrics, the business KPIs. If it's number of users or profit or something that's directly related to the business, that's actually the best case scenario, because then there's no translation error. There's no loss in the translation from the business problem to your definition of metric. But like in machine learning, most of the time, you're lucky if you're in that situation. Most of the time, you have to use some kind of proxy metric that correlates with that business problem, because it's just not feasible to use the direct metrics. Had one example where the positive outcome for the business was something that happened in like 6 months' time, for example. So you can't realistically wait for 6 months before you get any reward. There's no point, because your agent would just never learn. You might as well just treat it as an ML problem at that point. So we had to come up with some other observations in the business, some other signals, some other proxies towards that business goal that we could use that had a much quicker feedback time. What else is important in there? I think the plateaus one is quite generally applicable, but it's sometimes quite hard to spot, actually, when you're working in the business domain. It's quite easy to see when you're working in like a toy domain. So by plateaus, what I mean is that if you move from one state to another, and basically, if you imagine that the goal, the reward is climbing up a mountain. If you're if you're trying to climb a mountain in the Lake District in the UK, the north of England, but you're in London and you're just deciding whether to go left or right, like there's really no difference in choosing between left or right. And actually, the agent is just going to spend a long time just randomly kind of wandering around this, nearly flat sort of reward plateau. So what you need to do is you need to think of different metrics. Okay, well, in this case, it's not just maybe using height as my goal metric. We also maybe need to use distance to where that height is located. The distance to the Lake District. And so then that you actually need to head in a certain direction, and that's a very clear path, a very clear reward that doesn't have a plateau. So quite often you have to kind of combine rewards in order to remove some of the plateaus in the reward there. Okay. Kind of talked a bit about that. Let's skip that. It's getting a bit long now. This is all like just on a general note, like this is all super interesting, but obviously there's a lot to it. Like this isn't a simple subject, and as you start working on your own problems, you will find that you have your own sort of specific challenges and problems. I mean, if you do like reach out, I'd love to hear about them. And of course, depending on what your problem is and in what domain you're in, you might see some of these issues, but you might not as well. You might have a really easy time. So it's quite hard to pick out like the key ones. I guess I've already covered like the top few. If you're working on the environment and you're working on figuring out how best to represent the state, figuring out how to do the reward properly, that's you're starting to get the most important elements in place. Okay, I'm going to skip a few of these now because these are all. Let's talk about this because this is quite fun. I was asked to talk about what happens when you go deep, and I've kind of never heard the phrase "go deep" before, and so I kind of reminded me of this. And if you're into like sort of mockumentaries, on Netflix, there's a comedy. It's like a Californian sort of two guys that are going around being silly, basically, but it's like a mockumentary, and it made me think of this. But it's really fun if you like that kind of thing. Going deep seems to be a bit of a new way of describing when to use deep learning, basically. And just to recap, deep learning is a technique for nonlinear function approximation. It's a way of learning a function, and it's really useful in reinforcement learning because the policy, the thing that actually makes the decisions, basically just a very simple function. It's observations in, function, actions out. So what we're trying to do is learn that function. And deep learning is especially applicable because it's super flexible, often too flexible, but it can adapt to all sorts of crazy functions. So the key point to note is that any research in ML that is related to deep learning is absolutely relevant to reinforcement learning as well, because these types of models are used all the time inside the policies and other areas, in fact. So yeah, why deep? If you have continuous observations, then you basically have to. You can't create one single state for a continuous space. There's an infinite number of spaces, so you have to do some sort of functional approximation there. So yeah, if you don't want to discretize your inputs, then you have to use function approximation. Sometimes the resulting models may actually be simpler than trying to do it discretely. Like if you imagine trying to discretize some complex, continuous, but single valued observation, it might be simpler just to have a very simple model in there that just approximates that single value. But also the one of the key reasons why it becomes useful actually is for generalization. So in general, you've got to be really careful with deep learning, but with all machine learning, the whole goal is to generalize across the gaps in the data space that you have. So you never have every single data point well sampled in the machine learning problem. So you rely on generalization to fill in those gaps. It's possibly even more important in reinforcement learning to generalize, because it's not just the immediate result that depends on that generalization, it's the future result as well. So in machine learning, if you've got a gap in your data, you do a bit of bad generalization and you produce a bit of a bad result. Like, okay, well, we've got a bit of a bad result that time, drops our metrics, our accuracy, whatever, but whatever, hey ho, we can improve it over time. In reinforcement learning, if you have a bit of a bad generalization, it could send you down the wrong trajectory and cause the entire trajectory to fail, to result in a failure state. And therefore it feeds back through all of those previous states, negative. And it was all because of just bad generalization at that one point. If it had good generalization, it might have ended up in the right place. So the consequences are higher, is what I'm saying. So that's why you've got to be really careful when you are using deep methods, because deep learning in general it really wants to overfit. But yeah, bear in mind that using deep learning is a tool. It's not. So there's even now, but also a few years ago when I was writing my book, everyone was titling it like deep reinforcement learning. That was the new thing, DRL, because it kind of enabled the ability to solve some of these Atari games and things. And obviously they were using video inputs, and so the domain was quite complex, and so you needed something like deep learning that had the ability to interpret such a complex domain. So that's why it was popular. But it became this thing where everybody had to use deep, and deep RL was RL. And it's not. Deep is just a tool. Deep learning is just another tool. It's another modeling technique that you can use. Not the only one. There are others. Might not even be the right one. But also there's bigger problems elsewhere. If you don't have your simulation or your environment set up properly, if you don't have the observations, if you don't have the reward defined properly, doesn't matter if you use deep learning at that point, it's still not going to work, because the fundamental MDP, the fundamental framework, is not organized in such a way that you will be successful. Okay, so yeah. Yeah. Okay. That'll do. Yeah. I'm going to assume you know all this for now. You've done this. You've seen lots of other videos. You know how to do deep learning. Okay. So let's talk a little bit about. That's quite complicated, but really interesting. Oh, let's just have a quick note on this. So obviously one really common question is, which RL framework should I use? And the challenge with that is that open source is changing all the time. You know, you look the next week and it's old and broken and there's 10 new frameworks. There's a whole wide range of ones you can pick. They're all very good and they've all had a lot of effort put into them and they're all really impressive. So I'm kind of a little bit reluctant to suggest any particular. I did write a blog about it, but it's a bit old now. It's a few years old and it doesn't even mention some of the newer ones. So, I mean, all I can recommend is what we use right now. We typically, for productionizing and like serious RL development projects, we use RL lib. And to be honest, we use RL lib probably more for Ray than we do the actual RL algorithms. Ray is a really nice distributed computational framework that allows you to manage experiments at scale, basically. It's got quite a nice interface, quite, you know, lots of helpers and functionality to help people do that. RL lib is the reinforcement learning library built on top of Ray, but it's kind of all written in you know, Python and PyTorch and stuff. But yeah, I do want to shout out for Stable Baselines 3 as well. That is a Python PyTorch re-implementation of a project that OpenAI did like 3 or 4 years ago, and it's much more readable, much easier to understand. So that's more like if you're interested in tinkering with the algorithms and just finding an algorithm. If you'd read a paper about PPO or something and you want to try PPO on something, then that's a great example because it comes with loads of examples, loads of documentation, but it's not as industrial. It's not ready for sort of industrial deployment or anything like that. Yeah. So we talked about a few of these in a little bit. I'm going to skip over them now because I've been too long and I think my video is about to run out. So really sorry, but I hope you've enjoyed it. There was a last little bit on safety RL and recommendations in RL. If you're interested in any of that, then do let me know. So this is the end of the second part of this talk. In the next part, I'm going to be presenting a few examples. There was one new example, a really fun one that I generated for ODSC. There's one old one, which I still think is quite useful, but basically it's a bit more of a deep dive into actually practical implementation of some of this stuff. It's still very domain dependent, obviously. But if you're interested in that, then do come back next week. I'll go through each of those notebooks in turn and walk you through them line by line. All right, now I'm just going to pause and have a quick sip of my drink, and I'm going to go to the questions or the comments. So just give me 1 second to try and find those in my UI. Whoops, wrong one. Okay, it doesn't look like we've actually got any comments today, so I'll leave it there. I'll maybe just show this slide to just recap the link to the book and link to the website and things. Obviously, if you've got any more questions that you haven't managed to ask today, then feel free to reach out over email. Thank you for bearing with me. Appreciate it's been a long one today. Yeah, with that, I'll say good night. Thanks a lot.